everyone, I'm Avinash. I'll be covering latest techniques of entity matching in NLP. I work as expert data scientist at TomTom. So, what's entity matching? So, I'll be covering that. Then I'll be covering what is the importance of entity matching, history of entity matching, how it's been evolved, then different entity matching models and how to measure success of entity matching, especially in business scenarios. And then I'll cover one tool, Entity Embed, which is open source tool for entity matching. So let's just start. So what is entity matching? So in literature, entity matching refers to the problem of determining whether two different data representations refer to the same real world entity. So I will, throughout this presentation, I will take this example of two records, two songs. So as you can see on the screen, we represent two songs with five entities, or let's forget the ID. We represent it with four entities. So the title is Me and Mrs. Jones. Second one is Me and Mrs. Jones, and in bracket you will see remix. Then there is album, composer, and songwriter. All these things, right? By looking at this, you can easily say like they are probably either same songs, or second one is probably just the remix version of it. But human beings are really good at interpreting these things. So these are two entities, and anything in real world, if you can represent it with, let's just say, finite set of attributes, then I think you can call it as entity. And there are a lot of use cases for this, especially in NLP world. So if you have two songs like this, you can use entity matching for like comparing whether they are same or not. You can do same for address matching. And if you go to social profiles like Facebook, Twitter, or LinkedIn, you can pick up any user with like bunch of entities, a bunch of attributes, and check whether they are same or not. You can do that for close matching, or for that matter, I think any product in retail you can do entity matching for that. You can similarly do that for dating profile matching, or even to find out two people who have quite similar interests. So there are a lot of use cases. Anything that you can represent with finite attributes, you can use entity matching there, and I think you can just good to go. So yeah, so in this example, you can see the two songs are represented with like very well formatted things. All the data is there. But in real world, when I did my entity matching, like things got little bit complicated, and these are the problems I faced. So I'll be sharing that. So it's not always like that. It's not always that we use standard English or written English while we write down things in data. So a lot of people do data entry in like various areas, or we do OCR nowadays. So you will see a lot of use of words which is in colloquial fashion. Like if you go at row 4 or row 3 rather, you will see the word blowing is written as blowing. So that would be there. You will see some additional information like the word remix. You will see unnormalization of data. You will see unstructured data. Like sometimes you might see a composer present there, or it might be that the composer is written in a songwriter's place. It could go anyway. There will be missing data always. This happens always. There is dirty data, and more often than not, there will be unavailability of supervised data. So these are the different problems in entity matching. And the most important one is scale. So let's just say you have 1 million entities, like 1 million songs. Now you want to find out all the duplicate songs which are duplicates of each other. So there could be like 10 duplicates of one song, or there could be just two, or there could be like hundreds. So the best way, or the easiest way that you can do is you pick up one song, and then you will compare it with all the n minus 1 songs. Then you will pick up second song, and then you will compare it with all the n minus 2 songs. So for 1 million songs, that number of comparisons, that would be really huge, right? So like it would be for n songs, it's basically n into n minus 1 by 2. So if you want to do that kind of comparisons, the time and the number of resources that you're gonna require are really huge. So this is not the approach that we use nowadays. So we use something called as blocking. So instead of doing all the handshakes. So like this problem is called as handshaking, right? Like how many handshakes can be there. So if you want to avoid all this, what you would do is out of these 1 million songs, you will create some blocks of songs. So this is called as blocking. So what is a block of song? What would be the characteristic of this? So you create a block by doing minimal comparisons. You still have to do it with all the other songs, but you won't do rigorous or computationally expensive comparison. You will see, okay, there this might be a potential match, so you will just find out potential matches within a block. So one block will have potential matches, the other block would have their potential matches, and so on. And this is something that you achieve with high recall. So we call it high recall because anything, so let's just say you have a block, right? And it has 10 songs in it, and you can say that okay, they're potential matches. Now while training, you can actually verify whether that block is created correctly or not. So if you say you created a block with 10 records and only 7 are matches of each other, but 3 are random ones, so we'll say okay, my recall is 70%. So I mean, you obviously calculate for the all blocks and then add up, but I would say okay, for this block at least my recall is only 70%. So in this blocking step, you would focus on 100% recall. So no duplicate of any song in that block be present in any other block. So that is the objective in the first step here. So what are the things that you focus on when you're doing on blocking? So you will just create a block with high recall. Then also the number of candidates within that block should be as small as possible. While you still want to achieve a high recall, you don't want to increase the number of comparisons. So like worst case would be you create a block out of all the 1 million songs. So that would still be wrong. You will still have a lot of comparisons to do. So you create a small block as small as possible. So this is called as pair entity ratio. So basically how many pairs you want to create out of that block, that also should be small. And third one is you want to spend as minimal human effort as possible, and ideally it should be none. And obviously your blocking algorithm should be in a way that it can be applicable to millions or billions of records possible. So that are the things you would want to focus when doing blocking. So we'll cover blocking in detail first. So let's just look at two examples. The left one is without blocking, the right one is with blocking. So without blocking, you start with n songs, and with blocking, you're also starting with n songs. So when you apply computationally expensive comparisons with each pair that you could create, possibly create with out of these n songs, you are doing NC2 rigorous computationally expensive comparisons. But with blocking, you're doing minimal comparison and then creating small blocks. And then you are creating each block of size K. And let's just say there are M such blocks. So then essentially you are having KC to M rigorous computationally competitive comparisons. And initially you will have an minimal comparison. So minimal comparisons could be so minimal that that those could be done within seconds. So if you take n as 10 and you do without blocking, so you are essentially doing 45 expensive comparisons. If you again 10 n is equal to again take n is equal to 10 and do basically, let's just say, create small blocks of size k is equal to 2, though there will be like 5 clusters. So essentially you are doing one comparison within one block because there are only two songs, right? So 1 into 5. So basically only 5 comparisons. So 45 versus 5 rigorous comparisons, computationally expensive comparison. That is a huge difference. Hence blocking is important. So okay, so let's just dive into what is the history of entity matching. So it's, you can already guess. People would do pattern matching or fuzzy matching in the beginning. Then obviously you would use deep learning techniques, and then you could use a lot of transformers for maybe creating let's just say different kind of features and all. So I'll start with pattern matching, what we used to do initially basically. um, so let's just look at example. You are again seeing two songs and they are very well represented. So if you want to do song matching, for example, song as an entity, so what you would do here is you will probably match title with title, album with album, composer with composer, songwriter with songwriter, and you would create a specific pattern for it, or you would create. So basically, generally, whenever we write patterns, you would say, okay, if these things include these things, then you'll say, okay, they are matched. Or you can say, okay, if this excludes this, then they are probably not matched. Something like that happens. Now let's just say you don't have composer in record 2 and songwriter in 1. So now you will have composer in 1 and songwriter in 2. So when you do match Michael Bublé with space or nothing, and then in songwriter you would match Michael Bublé with nothing, right? I mean, that creates problem. So what you would do in pattern matching, okay, you will also compare composer with songwriter now. Now, these are just four entities. Imagine if it increases to 50, your number of combinations or like number of, I think, different kinds of pattern that would write would has to be a really lot. So the point is, when you use pattern matching, and as in you get like new records every day, you have to write, potentially write new patterns. If you want to support a new attribute, you have to write a new pattern. So things will keep going on. So basically, it's an incremental update approach. So a lot of maintenance cost is there, and it's not maintainable, as well as I think it could go haywire after like few iterations of pattern matching. So I would say don't do pattern matching or fuzzy matching when you do entity matching. So what what is the like one of the good approaches? So you can go with something called as deep learning based approach. So this would I'll cover this in 5 steps. So what would we do? So if you have a song like this, so we have forget about the ID, title, album, composer, and songwriter. Now, in first step, so this deep learning based blocking approach that I'm describing, it is from a paper called as Auto Block, and so the this diagram you see, it's what they have used. So I'll be explaining the same, and there are other techniques also, but this one I found interesting and very scalable. So in first step, you would do take token embedding. Now, if you go back to this example, so you have like each token would be me and Mrs. Jones. These are like 4 tokens. So you would do token embedding. Now there are a lot of different techniques available for token embedding. You can go for bag of words, or latest. You can use BERT for embedding. In this paper, they use fast text. The reason they use fast text is fast text supports something called as n-gram embedding. So now even if you have misspelled words, or even if you have incomplete words like blow in versus blowing, so I think fast text would cover that. So that's why they go for fast text based token embedding. Now attribute embedding. So the next step would be, once you have, let's just say for a title, you have created all the token embeddings, you want to combine them. So this is covered in attribute embedding. So you use basically attention-based neural network to combine them all, and you would obviously focus on certain tokens versus other tokens. So that is why the attention-based neural network is used. Then the most important step would be tuple signatures. So to give an example of tuple signature, let's just say you have title, your song name, then you have let's just say composer, songwriter, singer, maybe other artists, like a bunch of artists, 5, 6 artists of attributes of artists. Now, as we have seen, some artists could be present, some could be missing, like composer could be there. Sometimes it could be same, sometimes it could be different. So what tuple signature allows us is, you say you want to combine all these attributes together, create one signature, and when you create that one signature for one, let's just say record, when you create another, the signature for second song, let's just say, which you are comparing against, you are again combining them. So when you do the matching, even if your composer is absent but the songwriter is same, right? That helps in matching. So when you do the comparisons, you will get a better similarity than you would do in pattern matching. So that's why the tuple signature is something important. So you can also do tuple signature in other ways. So one way, one interesting way would be you just keep all the attributes as it is. That like those could be n signatures, and then you create other signatures, like you combine attribute 1 and 2, 2 and 3, 3 and 4, something like this. So there are a lot of approaches you can use, or you can use it as hyper parameter also. So that would also help improve your matching. Then next step is obviously model training. So this approach particularly requires this is a supervised approach, so you need a label set, and model is trained basically to maximize the differences of cosine similarity between the tuple signatures, between the like basically match pair. So in a way, if you have two songs which are match of each other, they will be placed together, and whichever are different, they will be put away of each other. Similarly, you represent your embedding in hyperspace the same way, and then you do fast and then search. So it just basically you take n as 100 probably, because that's what I have used, and then find out the potential. So this is what blocking is basically, the final thing in blocking. You find potential matches. Let's just you want to go with, so if you know your data set and you know, okay, there could be potentially 10 songs that could be a perfect match, and you know there are obviously always some outliers, but you might want to ignore them to get the best results. So we'll say, okay, I say n is equal to 15, and then you do fast and then search, and you are getting good recall on that, or better recall at that. So you will go for um, fast and then search with maybe 15 nearest, finding 15 nearest neighbors. So again, that could be one of the hyperparameters you want to use while training. So this is how the blocking would be done. Now, this was using deep learning now, and a supervised data set. But what if you don't have positive label set and you still want to do blocking? So there is one technique that I read in one paper. What they do is they use autoencoders. So basically, you have one song, you pass it through the encoder, then you will get a latent space representation. Here it will be UT, and then you use a decoder and extract and try to recreate the same song, the same attributes out of that. So song, then latent space representation, and same faster blocking. So if you have a smaller version of that song, then the matching would be faster. So that this is one way to do it. Um, yeah, so now blocking is done. What's next? So you are free to do computationally expensive comparisons. So you have 1 million songs initially. You did, let's just say, a minimal comparisons and found out potential blocks. Now you want to rigorously check whether this is a perfect match or not. So now the number of features you can use is just like limited by your imagination. So the simple ones that I referenced, like in one of the Kaggle competition I've seen. So they use edit distance between strings, embedding distance between different attributes. Then could be phonetic similarity. Then the length of the attribute. If you want to do attribute-wise comparison, you can use Jaro-Winkler similarity, sequence matcher, Jacquard, entity-specific features like let's just say if you have a song, then you can create like different features like the different notes used or the tempo of it, or maybe release date. Like you can create now thousands of features out of the song and do rigorous computations, because these comparisons would be done within the smaller block. So even if you do like rigorous comparisons, still the number of comparisons done out like throughout the I think all the songs when taken together, it will be still less because you're doing blocking in the first place. So that's it. Now the next step is how to measure success of entity matching. So how to measure success, I think this is the most important part, because if you want to do it, you suppose you should definitely have a metric in place and then go for experimenting with different models. So when you do training and you want to compare your different models together, you can definitely go for something like precision and recall, that is there. But you should definitely have a business metric as well. So let's just say you are doing, you're matching your different products, okay, and your products are represented with different attributes. So your business metric could be now your inventory is supported by these different products, and you have a mechanism to reorder, to pre-order those products. So if you have a duplicate products or duplicate entities, there might be duplicate pre-orders, right? That could be potentially you do the manual verification of those. So one metric could be, if your duplicate pre-orders were 100 in the beginning, now you do your product matching and remove the duplicate products. So your duplicate pre-orders are reduced by, let's just say, 50. So you can say, okay, my business metric here would be reduction in number of duplicate pre-orders. So we'll say, okay, my model is because of my model, the number of duplicate pre-orders are reduced to half. So that's a big success if you look at, if you like check for any logistic company. Let's just say even if they have a manual verification, you are saving those efforts. Even the manual verification could be faulty also. So that is one very good way of using entity matching, and this is a very, I think this is very important to have a business metric, because even if you do use it for entity like deduplication or finding similar entities, how it impacts your business is of utmost importance. So now, can we know if we did the perfect entity matching? So in case of this product deduplication, can you say that I don't have duplicates at all in my, let's just say, a set of 10 million products? You can never say that. There is no way of saying that, okay, there are no duplicates. Even if you do manual verification, I think the manual verification is impossible here. Even if you use, like, do entity matching 10 times or 100 times or use different models, there is no way. Because if you had a way of saying that there exists a duplicate or not, you would have used that method, which in first place you're used to find out whether there are duplicates or not, right? So there is no way. But definitely having business metric and these other metrics help. um, you can alternately or additionally use human in the loop techniques. Let's just say you have a pair, and then you used, so you did blocking, you used rigorous, let's just say this, you created a lot of features, hundred of features, and then you, let's just say, use light GBM on it. So you will get a confidence of uh, the, like, how similar are these two entities, like percent of it. So you can say if something lies between gray area, let's just say 50% to 80% or 70%, you can use human in the loop for that. And whatever is above 80%, you can surely say, okay, these are my perfect matches. So the threshold could vary, but that's the idea. So applications of entity matching, again, just to reiterate, you can match songs with that. You can do address matching, social profile matching, clothes matching, or product matching, matrimony and dating sites profile matching. So there are a lot of ways, just limited by your imagination, I would say. So there is interesting tool which is available with Python also, which is called as entity embed. You can install it with just pip install entity embed, and you will be done. It needs some data preparation. So it represents each entity with a list of dictionary. I mean, all the entities with list of dictionaries. So each record, I will call it as this small dictionary, is a record. It needs ID and cluster. So ID is basically, you have 1 million songs, so you can represent those songs with ID between 0 to 999 and whatever that number is. So cluster is, so this is for supervised again. So entity embed is implemented with the same logic that auto block has talked about. So it follows that. So cluster means, so if you look at these first two examples, so cluster is basically zero for both. So it means they are duplicates of each other. Since it is supervised, you would need that cluster also, cluster ID also. And then there are other things. So you represent title, artist, album with different, uh, basically as keys in a dictionary. Now other things, defining the fields. So you want to with this tool, Entity Embed provides how do you want to encode these fields. So you can use the default tokenizer of Entity Embeds. You can use something called as multi-token. So this field type is multi-token. This field type is semantic multi-token. So how they are going to be embedded. So that is also you can specify here, and even the what kind of vocab should be used you can specify, but just be careful that what you are mentioning here should be used for prediction also. Then yeah, so entity embed under the hood uses pytos, lightning. So you have to use the data model object, and you pass basically three types of dictionaries while training. So basically trend record dictionary, validation and testing. And then you have to specify the numericalizer. The cluster field is basically the field which identifies what are the duplicates of each other. So and what are not the duplicates of each other. So the in the example you have seen cluster 0 and 0, they are duplicates of each other. And then there are these other the hyperparameters. Then you actually train the model, and you can specify um, whatever approximate nearest neighbor, how many ever you want to find out, that you can specify and experiment with. And then actually after the training you want to predict, right? So when in production you have the access to model, and you can use predict method, which basically will give you the embedding version of your songs. But if you want to find out the neighboring pairs, you use predict pair method for this tool. So that is how you will get the so the way it will be used in production, let's just say you trained it on let's just say 10 billion or 1 billion songs. Now new song comes in, so you create a record dictionary for that song, which will have just one song, right? Then you say predict pairs, and ANN is equal to 100. So it will find out all the songs that you trained your model with basically in that space, and it will find out the 100 duplicates of the songs. So these are the references I used. So deep learning for blocking and entity matching. So this is one paper. Auto block is another paper. Entity embed is the tool, and location matching. Basically, it was I think Foursquare's competition on Kaggle. So this is it, and I'm open for questions. So yeah, thank you guys for listening. Do you have any questions now?
Hi. Hey, Avinash. Yeah.
Yeah.
Are there any questions online, offline? No, I think that's it. And we actually don't have too much time. So
Oh,
thank you, Avinash, for that wonderful talk. I hope you had fun preparing it and sharing it with our audience online and here live at the Youth Center.
yeah. Thank you, everyone.